All right, so the astronomical coordinate systems. So we're going to be talking about things that are similar to our geographical coordinates, but they deal with the celestial sphere as opposed to the Earth. And there's two sets of astronomical coordinate systems. There is the horizon system and there's the equatorial system. And we're going to start by talking about the horizon system of celestial coordinates. And they are made up of altitude and azimuth, where altitude is the angular distance that an object is above the horizon. So how many degrees above the horizon something is. And your altitude ranges from 0 degrees at the horizon to positive 90, which would be at the zenith directly overhead. And for objects that are below the horizon, altitude will range from 0 to negative 90, which would be the nadir, directly under your feet. The second coordinate for the horizon system is azimuth. Azimuth is the angular distance around the horizon. So if you think of the horizon as a circle that's made up of 360 degrees, how far around, starting from north, due north is what we make 0, how many degrees around that horizon circle something is. And yeah, it ranges from 0 to 360. So you can kind of see in the picture, again, how far around the horizon, that's your azimuth. And then how many degrees high up in the sky is your altitude. So we're going to write down the altitude and azimuth measurements for a variety of things. I think this table is on the second page. So for any of the cardinal points, north, east, south, and west, altitude is always going to be 0 because they exist on the horizon. And the horizon is our 0 altitude. North is defined as 0 degrees azimuth. So our degrees around the circle of the horizon, we always measure starting from north. Likewise, east, again, 0 degrees altitude, but you are a quarter of a way around the circle going from north. So it has an azimuth of 90 degrees. West, or no, south. South, you are halfway around the circle of the horizon. So south is 180 degrees azimuth. And once you hit west, you're 3/4 of your way around the horizon circle. And so the azimuth of west is 270 degrees. And again, for all the cardinal points, altitude is 0 because they exist on the horizon. Because altitude is how far above the horizon something is. Your zenith, remember, zenith is the point directly overhead. So the zenith will always have an altitude of 90 degrees because it is right above you. Azimuth isn't needed for zenith because, again, like zenith is wherever you are, right above your head is your zenith. So zenith only has an altitude measurement, which is 90. The North Celestial Pole, or the NCP, has an altitude that is going to be equal to its latitude. So for us in Grand Ledge, the NCP is going to have an altitude of 43 degrees above the horizon. And it has an azimuth of 0. Because again, if it's the North Celestial Pole, it should be due north. And north we define as 0 degrees azimuth. Star rise, so where you would expect stars to rise, again, it's always going to have an altitude of 0 because they'll rise starting at the horizon. And azimuth is going to range anywhere from 0 to 180. So anywhere from due north to due south is where you're going to see stars rising. And star set is the opposite half of the sky. Again, still an altitude of 0 because it's at the horizon. But then you're going to see stars setting anywhere from due south to due north, 180 to 360 degrees azimuth. Because 0 and 360 degrees azimuth are both north. They are both due north. And lastly, an upper transit. Again, remember the definition of an upper transit is when a celestial object crosses the astronomical meridian. So that's when its altitude is going to be its highest. It's going to be at its highest point in the sky. And azimuth, similar to star rise, is going to be anywhere from 0 degrees to 180 degrees azimuth. So upper transits will be anywhere from directly due north to directly due south. Are you okay to move on? Okay. One more thing we have on this page. 1 degree is also equivalent to 60 minutes of arc. And similar to what we would expect for time, 1 minute of arc is equivalent to 60 seconds. Okay, so now we're going to talk about how you can figure out sunrise or sunset azimuth. So remember, altitude is how many degrees above the horizon a star is, and azimuth is just how far around the horizon it is. And again, the cardinal points, north is 0 degrees azimuth, east is 90 degrees, south is 180, and west is 270. Now, things to remember, the sun's position where it rises and sets shifts slightly over the course of the year. The sun is always going to set north of the east and west points on the horizon during the spring and summer. So approximately March 21st to September 21st. So in the spring and summer, the sun sets slightly to the north of east and west. The opposite occurs during the fall and winter. The sun will set to the south of the east and west points during the fall and winter. So roughly September 21st to March 21st. And we should recognize something significant about these dates, March 21st and September 21st. Who can remember what those dates are referencing? Yes.
The summer solstice, or the eclipse, or not the.
You're thinking of the equinoxes,
Yep.
And that would be correct. March 21st is the date for our spring equinox or vernal equinox. September 21st is the fall equinox. And that's because on the equinox, the sun will rise and set, excuse me, directly due east and directly due west. So every other part of the year, the sun is either going to be setting slightly to the north or slightly south of east and west. But on the equinoxes, the sun will rise directly due east and set directly due west. All right, so now we're going to draw a diagram that's going to help us with when we have to do some calculations. So the first thing that I'm going to mark on this circle is I'm going to mark the cardinal directions. So I'm going to put north at the top, south at the bottom, east on the right, and west on the left. There we go. Okay. So for north, that's going to be 0 degrees. East is 90 degrees. South is 180 degrees. And west is 270 degrees. Once I have the azimuth degrees marked, I'm going to draw a dotted line from the west to the east point. That's going to kind of be my little divider. And at the top, I'm going to write spring and summer. Roughly March 21st to September 21st. Because we know that the sun is going to rise and set to the north of east and west in the spring and summer. So that's why I drew that on the top towards north. We're going to put fall and winter on the bottom. Roughly September 21st through March 21st. Again, because we know the sun sets to the south of east and west in the fall and winter. Now, it's the next part of this that makes it really helpful for when we have to do sunrise and sunset azimuth calculations. If you're trying to figure out sunset in the spring and summer, we're going to add. And if you're trying to figure out sunrise in the spring and summer, we're going to subtract. And it's the opposite for fall and winter. If you want to figure out sunrise in fall and winter, you're going to add. And if you want to figure out sunset in fall and winter, we're going to subtract. And we'll let everybody finish getting that written down, and I'm going to also put it on the board over here so we can just have something that can stay up for us. All right, let's do some practice problems now so we can kind of see how this diagram works. So our first question says, if the sun sets 10 degrees away from due west, so 10 degrees away from west on October 20th, what is the sunset azimuth? So first off, are we dealing with spring, summer, or fall, winter? Fall, right? So we know this is the fall. And if it's the fall, we know the sun is going to be setting to the south of east and west. So the sun is 10 degrees away from west. So we know west is 270 degrees azimuth. And if it's setting in the fall and winter, we need to subtract 10 degrees from west. So minus our 10 degrees, to give us a sunset azimuth of 260 degrees. Our second question says if the sun rises 12 degrees away from due east, so 12 degrees away from east on April 19th, what is the sunrise azimuth? So April 19th. Well, first off, are we dealing with spring, summer, or fall, winter? Spring, right. And in the spring, we know the sun is going to rise to the north of east. Well, east has an azimuth of 90 degrees. And if it's rising in the spring and summer, we're going this way and we're going to have to subtract again. So 90 minus our 12 degrees gives us a sunrise azimuth of 78 degrees. Questions on how I use the diagram to figure these out? All right, so altitude and azimuth are a nice coordinate system because, you know, conceptually they're easy to visualize. So degrees above the horizon, degrees around the horizon. However, it's kind of problematic because altitude and azimuth measurements are dependent on time and location. Because the stars change their position over the night with respect to the horizon, and stars' positions will be different if you view them from different locations, right? Like we said, things like the NCP and Polaris, well, their azimuth is going to, or their altitude is going to be dependent on your latitude. Which, like I said, this is going to mean observers in different locations who are looking at the same star are gonna, even at the same time, will have a different altitude azimuth position. So this is problematic from a scientific point of view, because when you want to talk about where to find something, right, you want to be able to use language and positions that anybody anywhere is going to be able to find. So that's going to make it, when you do experiments, it makes it easier for people to verify the results of your experiment. If you can, you know, easily, if they can easily compare their measurements to yours. So astronomers typically do not use altitude and azimuth. They use the equatorial coordinate system. And the equatorial coordinate system is really nice because it is a fixed system with respect to the stars. So it doesn't matter what location you're at, it doesn't matter what time of day or night it is, you're always going to have the same coordinates in the equatorial system for a star. It's very, very similar to the latitude and longitude lines that we have on the Earth. It's just we've taken the idea of latitude and longitude and we've projected it onto the celestial sphere. So when we talk about this system being fixed, what do we mean by fixed in this case? Yes. Not changing. So when we say this, the equatorial system is fixed, we mean that it is not changing. So there are two types of coordinates with the equatorial system. There are lines of right ascension, commonly referred to as RA, and there's also lines of declination. We're going to talk about right ascension first. So they are lines of right ascension are like your longitude lines on Earth. And right ascension is measured in terms of time, so hours, minutes, seconds. And it increases as you move in an easterly direction. 0 RA, or zero right ascension, is defined as the point where the sun crosses the celestial equator at the vernal equinox. So unlike lines of longitude on Earth, where we just kind of arbitrarily picked what would be 0 as the prime meridian, when it comes to the equatorial coordinate system on the celestial sphere, your 0 RA has a very specific definition. And this specific definition is part of what allows this to be a fixed system. So a fixed coordinate system where your coordinates don't change like they do for altitude and azimuth. And we'll look at a diagram in a second, and so it'll be a little bit easier to see, where the sun crosses the celestial equator at the vernal equinox. So here's our diagram. Oops. And so this is a diagram of the celestial sphere. So at the top is the NCP, at the bottom is the SCP, and right through the middle is the celestial equator. Now, this line coming right here at an angle is labeled the ecliptic. That's what we call the path of the sun. And so at the point where the ecliptic, the path of the sun, intersects the celestial equator, this is the RA line that is defined as the 0 hour. And so time increases as you move in a westerly direction from the 0 hour around the celestial sphere. Another thing to note, the full 360 degrees of Earth's rotation is broken into 24 hours. So the 24 hours of our day. So that means roughly 1 hour of RA, 1 hour of right ascension, is equivalent to 15 degrees of rotation for the Earth. Now, that sounds like then, if two stars are 1 RA apart, they should be 15 degrees apart. Not always true though, because just like lines of longitude on Earth, RA converge at the celestial poles. So they're going to get closer to each other the closer you are to the celestial poles. So if two stars are 1 RA apart on the celestial equator, then they will be 15 degrees apart. However, if they are 1 RA apart, like in the circumpolar region, they're going to be a lot closer than 15 degrees together. The other coordinate in the equatorial coordinate system are lines of declination. And lines of declination are kind of like the latitude lines on Earth, in that they run east-west and are parallel to the celestial equator. And also similar to latitude lines on the Earth, declination is measured in degrees away from the celestial equator. So your lines of declination are always measured in degrees north of the celestial equator or degrees south of it. So lines of declination are easier to remember because they're almost exactly like latitude lines on the Earth. So the last thing we're going to talk about today is an effect called precession. And so precession, in its most basic form, is what we call the wobbling of Earth's axis. So we know the Earth's axis is tilted. It's part of what gives us seasons. However, the Earth rotates and it revolves around the sun, but it also wobbles on its axis ever so slowly. because it's a little bit like a spinning top. The Earth isn't a perfect sphere. It's a little bit lumpy and it's got a kind of a bulge at the equator. This equatorial bulge is pulled on by both the sun and the moon. And these opposing forces on the Earth are part of what makes it wobble, particularly the moon, because the moon doesn't orbit the Earth in the same plane. The moon's orbit is slightly tilted with respect to the Earth. So the moon kind of orbits the Earth more like this, rather than like this in a flat plane. But we'll talk more about that when we talk about the moon. But because of these opposing pulls on Earth's equatorial bulge, the Earth is a little bit like a top. Tops don't typically spin perfectly like this. There's a little bit of wobble with the axis. And this wobbling is what we call precession. And the Earth's axis completes one full wobble once every 26,000 years. So it happens very, very slowly. This does mean, though, however, the poles of the Earth point in slightly different spots over time, which means Polaris has not always been the North Star. In fact, about 14,000 years ago, Vega was the North Star because Earth's axis was pointed in a slightly different direction. And that'll happen all over again as time slowly goes on. Questions on precession? Okay. Yes.
So you said that it like wobbles, but it also rotates on its axis.
Yes.
And if it's wobbling and it's like becoming unaligned with Polaris, if it's also rotating on its axis, how does it not become unaligned?
So when I say it's rotating on its axis, I mean like Earth's spin.
Right. Yeah.
So like what gives us its day.
Yeah.
So it's spinning, but it's also moving like this ever so slowly. Once every 26,000 years, it'll go like this.
Okay.
And that slight difference in where the pole points will determine what is our North Pole star, or if we have one at all at a particular time period.
Okay.
Good question. Other questions about precession? Okay.